Alright, so last time we talked about heat and how it's related to temperature change. If there's no phase or chemical change involved, we said that heat is just directly proportional to the temperature change, right? Q is just C times delta T, where C is the heat capacity. And we define specific heat as the heat capacity per gram. So specific heat is represented by the symbol S, if we use S, or C sub S, okay, or a little small c, okay. It will just be the actual heat capacity divided by the mass m, all right. So how do we measure specific heat in the lab? We use an insulated apparatus called a calorimeter, okay. And the idea here is that in a calorimeter is insulated, thermally insulated. So Q, the total Q for everything inside the calorimeter is going to be equal to 0. All right, so your system in this case would be the hot object and the cold object that you mix inside the calorimeter. So what you do is your unknown object would be one of these two. So you have two things you're going to mix inside the calorimeter. One with a known heat capacity, the other one with an unknown heat capacity. Okay? So the two together would be your system, but you have to take into account the fact that the calorimeter is not really just going to stay there and do nothing. So it's going to absorb part of the heat if the temperature goes up, or it's going to release some heat if the temperature goes down. So you have to take into account the effect of the calorimeter on the entire process. So Q for the rest of the calorimeter, okay, is heat capacity of the rest of the calorimeter, Ccal, times the change for the rest of the calorimeter for change in temperature. Ccal, right here, is called your calorimeter constant. So that's the heat capacity of the immediate surroundings of your system being studied. So that would be the container, the thermometer, the stirrer, and the air above your system. Okay? So everything else that's inside the calorimeter, we can lump it all together and have a heat capacity for all of those, and we call that your calorimeter constant. All right. So in what we call a standardization run, okay, the first thing you need to do in a calorimeter experiment is to determine this calorimeter constant. So when you do a standard run, you mix two things. The hot object and the cold object would have a known heat capacity. So if you can measure delta T then for both objects, then you know the Q for both of them. So you will know Q system. So when you do a standard run, Q system is known. Okay? It can be measured it can be easily calculated from the measure delta T. Delta T cal can be measured, so in a standard run, your purpose is to determine the calorimeter constant. And then later, okay, if you have an unknown object now, your unknown, okay, let's say one of these two would be unknown, so Q for one of those two would be unknown, but you would already know your C cal and your delta T cal. So let's illustrate that with a couple of problems. Let's say you have a 70-gram sample of metal with a known specific heat of 0.300 joules per Kelvin per gram, and the metal is at 100 degrees Celsius. You have a piece of metal at 100 degrees Celsius, 70 grams. You're going to pour that into a calorimeter containing 100 grams of water at 20 degrees Celsius. Okay, so, and your final temperature is found to be 23.0 degrees Celsius. Right? So our goal here is to determine the calorimeter constant. So what's the equation that we have to use? We're going to say Q of our metal plus Q of our water plus C cal delta T. What's that going to add up to? Q for everything inside adds up to 0. Okay. In a calorimeter, all the Q's add up to 0 because your calorimeter is an insulated container. So any heat loss by any part anything inside the calorimeter has to gain by some other thing inside the calorimeter. So what's the formula for Q metal? Mass of the metal. So I'm just going to call that M1. Specific heat of the metal, I'm going to call that C1. And delta T for the metal would be T final minus T initial for the metal. Okay. Q water would be what? Mass of the water, so I'm going to call that M2. Specific heat of the water, C2. And then T final minus the initial temperature of the water. Okay. And I have, what's my C cal going to be? It's my unknown, right? So plus C cal times T final minus T initial of the calorimeter. What's the initial temperature of the calorimeter? Well, the calorimeter and the water were together to begin with. So the initial temperature of the calorimeter will just be the initial, same as the initial temperature of the water. So T initial for the water. And all of these should add up to 0. So how do I solve for C cal? C cal, okay, let's go back to this one simpler equation right here. Solve for C cal. What would it be? Move this to the right and that to the right also. So that's going to be what? Negative of Q metal plus Q water divided by delta T cal, right? So what's our Q metal? Let me use MathCAD for this one. Make it faster. Let me see. So what is our formula? C cal equals negative Q metal plus Q water divided by delta T cal, right? So it doesn't know what those are, so let's define what Q metal is. Q metal equals mass of metal times specific heat of the metal times T final minus T initial Ti metal, right? And it doesn't know what those are, so let's define what's the mass of our metal. Mass of the metal equals, what was the problem? Mass of the metal was 70 grams, okay? 70 times grams. Now, MathCAD doesn't like, uses GM as abbreviation for grams, because when you use G in MathCAD, that's a predefined symbol for acceleration due to gravity. Keep that in mind. Okay, so mass of metal is 70 grams. What's our specific heat of the metal? That was given. How much was it? 0.300 joules per Kelvin per gram. So 0.300 times joules per Kelvin per gram. Okay. And our mass, let me get the correct sig fix there, 70.0. Okay. And what's our T final? Our final temperature was 23.0 degrees Celsius, so let's make that Kelvin. So 23.0 plus 273.15 Kelvin. Okay. What's my T initial? T sub I Ti metal equals 100 degrees. 100 degrees Celsius, the initial temperature of the metal. So that's going to be 100 plus 273.15 Kelvin. Let me fix this up. Format, align regions, down. Yeah, there it is. Okay, so now it knows what Q metal is. Let's verify. Q metal equals, that's the unit in, okay. Oh, we don't know what C is. We do know mass, metal. Okay, it should be in joules. Okay, your units are not consistent. What happened here?
C metal, yeah, G, not GM.
Oh, okay, see. That should be gram, not G. Okay. Yeah, gram. There, that's the right unit now. So your Q metal is negative 1.617 times 10 to the third joules. Right? And we do Q water. Q water equals mass of water times C of water times T final minus T initial for water. Okay? It doesn't know mass water. What's the mass of our water? 100 grams of water. 100.0 times Gm. Heat capacity of water equals 4.18 joules per Kelvin per gram times joules times reciprocal Kelvin times gram reciprocal. And what's the initial temperature of the water? Initial temperature of the water is 20 degrees Celsius. So I'm just going to say that's 20.0 plus 273.15 Kelvin. And so I have my Q water. Okay, do these numbers make sense? 1600, negative 1600 for metal, positive 1200 for water, just approximately. Positive 1300. So water gained heat flowed into the water, so you can see your Q water is positive, right? And Q metal is negative. But what happened here? The water gained more heat than the heat lost by the metal, right? Is that? Does that make sense? Oh, no, 1600 versus 1300. The metal lost more heat, right? 1600 is bigger than 1300. So more heat was lost by the metal than by the water. In fact, if you add Q metal plus Q water, what do you get? Negative 363. You have a deficit of 363. There's 360 joules unaccounted for. Where did that 360 joules go to? It was used to heat up the rest of the calorimeter, to heat up the air above your water and your metal, and the immediate the stirrer and the thermometer and immediate surroundings in the container the immediate surroundings inside the container of your water and your metal. So that's 363 joules. So what's our delta T cal? The same as T final minus the initial temperature of water. Remember, your water and your calorimeter were in the same. Your water was in your calorimeter to begin with. So T initial water. Okay, so now you can solve for C cal. C cal is minus a Q water plus Q metal over delta T cal. So C cal equals this. What should be the unit for C cal? Joules per Kelvin. Okay, so 121 joules per Kelvin. So that's how you determine your calorimeter constant. You run a process inside your calorimeter where you know all the Q's. So the only unknown there is C cal, delta C cal. You measure your delta T, so you can solve for C cal, calorimeter constant. Right? So the answer is 121 joules per Kelvin. Alright, so now that you've standardized your calorimeter, okay, you can now use it to make measurements. So here's an example. Let's say you have a 150 gram sample of metal at 100 degrees Celsius. You poured it into a calorimeter containing 100 grams of water at 20 degrees. You measured the final temperature of the mixture to be 24.5 degrees Celsius. So if the calorimeter constant is, let's say you've already measured it before, you found it to be 125 joules per Kelvin, what's the specific heat of the metal? So same equation here, Q metal, I'm just going to call it, okay, Q metal plus Q water plus Q cal, which is C cal delta T, right? Cal must be equal to 0. This time, what do you know? You know C cal delta T cal. You know Q water, right? You can calculate Q water. You can solve for Q metal. And once you know what Q metal is, what do? How do you get the specific heat of the metal? Q metal is mass times specific heat of the metal times delta T, right, of the metal. So you can divide that by the mass and the delta T. That would allow you to solve for the specific heat of the metal. So you can say, all right, let's do that on MathCAD. You can say that C metal equals, what's the formula? Q metal divided by mass of the metal times T final minus T initial of the metal, right? But our Q metal is going to be different. Our Q metal is going to be different this time. Let me just delete all these previous ones so we don't get messed up. Okay, so I know I have to calculate Q metal. What is Q metal? Equals negative of Q water minus C cal times T final minus T initial water. And Q water, I can just change this. C water times T final minus T. Okay, let me do it this way. I know Q metal is what? Negative Q water minus Q cal, right? So I'm going to substitute that for Q metal. Symbolic variable substitute. Okay, so that's my C metal, right? And what's the formula for Q water? Q water is mass water times C water times T final minus T initial water. So I'm going to copy that and I'm going to substitute that for Q water over here, variable substitute. And there's my equation. So C metal equals that. Okay. Let me clean that up. Okay. Do I have all the information I need? Q cal. Okay, I know my Q cal is C cal times T final minus T initial of the water, right? So copy that, and then I'm going to substitute that for Q cal. So I'm going to click on Q cal here, symbolic variable substitute, and there's my final equation. C metal equals that final equation. Okay. So there's my final equation right there. Get rid of the derivation there. So what's my mass of water? It's 100 grams. So 100.0 grams. What's heat capacity of water? 4.18 joules per Kelvin per gram. T final was, what's our T final? 24.5. So that's going to be 24.5 plus 273.15 Kelvin. And T initial water is how much? The water is initially at 20 degrees. That's 273.15 Kelvin. Okay, C cal is given as 125 joules per Kelvin. And what else do I need to know? Mass of the metal is given as 150 grams. And T initial of the metal is given as 100 degrees. So 100 plus 270.15 Kelvin. I got all the information I need. Heat capacity of my metal is, that's joules per Kelvin per gram, per kilogram. So I wanted joules per Kelvin per gram, so I'm going to say joules per gram. And that gives me joules per Kelvin per gram. 0.216 joules per Kelvin. That's the specific heat of my metal. Okay? Now, how are you going to make your metal at 100 degrees Celsius if you want to make this, if you want to do this experiment? You've done this in physics, right? You immerse your metal in boiling water because boiling water will be at 100 degrees Celsius. So leave it there long enough, it's going to be at 100 degrees. And then you transfer it to your... So if you want to do an experiment, a convenient way to get your temperature to 100 degrees or of your sample to 100 degrees or 0 degrees Celsius is to immerse it. If you immerse it in an ice water bath, you can keep it at 0 degrees. You immerse it in a boiling water, then it will, after a while, it's going to reach 100 degrees. Okay. Of course, you can just mix two samples of water, cold water and a hot water. You can monitor the temperature of those two. I think you did that in your freshman chemistry lab. All right, so that's how you would determine the specific heat. Okay, so throughout the process there, I just gave you the final answer here, but if you were to do some of these things step by step, along the way you'd figure out what is this? This is just Q cal, this is just Q water, right? And then this whole thing is just Q metal. And if you divide it by delta T of the metal, then that gives you the heat capacity of the metal. And then if you divide by the mass of the metal, you get the specific heat of the metal. Okay. So this is just nice. This is just what's the word? More elegant way of solving for what we really need. You just derive all the equations that you need into one final equation. Problem with this is if you make a mistake in your derivation, if you're doing it manually, then you're all messed up. But so if you have those intermediate values, you might be able to spot problems where you might get some unreasonable numbers. All right, so let's summarize what we do in determining specific heat. Like I said, you do a standardization run. Okay, so you can mix water with something that's known. So you mix water and water, okay, at two different temperatures, or you mix water and a known metal with a known heat capacity. So you know your Q water, you know your Q known, and M times specific heat times delta T is Q for each one of these, right? And then you can calculate Q cal, given the fact that Q water plus Q known plus Q cal is going to be equal to 0. Once you know your Q cal, you can solve for your C cal. Q cal is C cal times delta T. Delta T is something you measure. So once you know your calorimeter constant, you can do an unknown run with that calorimeter. So again, you mix your unknown with water, okay, and so that will give you Q for the water from the measurement of your temperature change. And then you know your Q cal, because your Q cal will just be the known C cal times the delta T that you measured. And then finally you can solve for your Q unknown. Again, the basic equation to know here is the sum of all the Q's is equal to 0. And you can solve for the specific heat of the unknown once you've done it. Now, a lot of times textbook problems ignore the calorimeter constant. Okay, will give you a problem to determine the specific heat, and it doesn't give you the calorimeter constant. In those cases, you can just assume that the calorimeter constant is 0. Okay. All right. How do we estimate heat capacities at constant volumes? For gases, okay, you can estimate heat capacities to be 1/2 R for each translational mode. What's a translational mode? What's translational motion? When molecules move from, or atoms move from place to place, that's called translation, right? If you have a molecule, in addition to translational motion, what does a molecule have? It can have rotational motion, right? Or it can have vibrational motion, right? So for each translational mode, how many translational modes does a molecule or an atom have? 3, right? Motion along the x-axis, motion along the y-axis, and motion along the z-axis. So if you just have a monatomic gas, okay, then your CV for a monatomic gas would be 3/2 R. If the only thing your gas particles are able to do is move from place to place, there's no rotation, no vibration, then your heat capacity at constant volume is 3/2 R. That's 1/2 R for each degree of freedom, for each translational mode. Okay. Now for each rotational mode, you get 1/2 R. You remember from last semester, you did, if you have a linear molecule, okay, then the rotational, you say that a linear molecule has 2 rotational modes, okay? When we did the transformation of coordinates from Cartesian for each atom into translational plus internal coordinates, you find that if you have a linear molecule, you're going to need 2 angles to define the orientation of that molecule in space, theta and phi. Theta is the angle with respect to the z-axis, right? And if you do a projection on the y-axis, on the xy plane, phi is that angle. And theta and phi, we use that to describe the rotational motion of your linear molecule. So there's 2 rotational modes for linear molecules. So again, it's 1/2 R contribution for each rotational mode. Okay? Now for each vibrational mode, at very high temperatures, its contribution is going to be R, but usually contributions of vibrational modes to heat capacities tend to be small at room temperature, so you can neglect this. Okay? So there's 3 translational modes, 2 rotational modes for linear molecules, and for non-linear molecules like water, for example, it's going to have 3 rotational modes. Okay? You're going to need to have 3 angles to define the rotation of a water molecule. All right, so the vibrational modes would be 3n minus 5 if it's a linear molecule. Why 3n minus 5? Well, remember, if you have n atoms in a molecule, let's say you have 3 atoms, Okay? How many coordinates do you need to describe the motion of the three atoms? If n equals 3, 3n would be 9, right? You can describe the motion of each atom separately. X, Y, and Z for atom 1, X, Y, and Z for atom 2, X, Y, and Z for atom 3. So there's 3n total modes of motion, you say. You need 3n coordinates to describe the motion of the atoms. Now, if instead of using X, Y, and Z, X, Y, and Z, and X, Y, and Z for the three atoms, we do a transformation of coordinates. We use center of mass coordinates and relative coordinates. Then what happens then is you would have 3 coordinates for the center of mass, right? So that accounts for translational motion. So the motion of the center of mass, we say, is the translational motion, plus 2 rotational modes for linear molecule. Okay, so you subtract that from the 9, so 3n is the total, which if you have a triatomic molecule would be 9 minus 5. So 3n minus 5 is the number of vibrational modes. Okay? So if you have a diatomic linear molecule, for example, what would it be? 3n minus 5. So 3 times 2 minus 5 is 1. 1 vibrational mode. The only vibrational motion of a diatomic molecule is stretching, right? Stretching. So a diatomic molecule would have 1 vibrational mode. Now, if you have a nonlinear molecule, okay, then you subtract 6, because 6, we have 3 translational modes plus 3 rotational modes. So from the total number of coordinates you need to describe the motion, you subtract 6, and that would take care of the number of vibrational modes. Okay. What are these vibrational modes? Might be a good idea to show you an old movie right now. Thing is, I can't get the volume on this. I've been having trouble with the volume on this one. Let me see if I can pull up that movie. But if I can't get any sound, I might as well not play it. Well, you can watch this outside of class. You do a search for Internet Archive. Let's see, that molecular motion, I think. Vibration of molecules, right here. Let me see if this is what I wanted. No, this is not what I want, but let's just do a search for animation of vibrational motion. Okay. Let's just say CO2. Vibrational motion of CO2. I don't have the plug-in for this one. There it is, CO2. How many vibrational modes does CO2 have? 3n minus, carbon dioxide is a linear molecule. So 3 translational modes, 2 rotational modes. So number of vibrational modes would be 3 times 3 atoms, right? Minus 5, 9 minus 5. That's 4 vibrational modes. Here are the 4 what we call normal modes. All the vibrational motion of a carbon dioxide molecule can be thought of as a linear combination of these 4. So you can call this the basis So those are called the normal modes. So you have asymmetric stretch, symmetric stretch, vertical bend, and horizontal bend. Okay. So those are the animations for the vibrational motions of your carbon dioxide. All right. So let's estimate heat capacity at constant volume for helium. What would it be? Helium, one atomic. Only thing it does is move from place to place. Translational motion, no rotation, no vibration. So CV for that would be 1/2 R for each translational mode, 3/2 R. So what would that be? 3/2 times 8.314, right? And the unit is what? Joules per Kelvin per mole. Let me write that. 3/2 8.314 joules per Kelvin per mole. So that's about 12 point something. Okay. What about CO2? So this is for helium. CV is approximately equal to 3/2 R is the contribution from translational motion. What's the contribution from rotation? 1/2 R for each rotational mode. So 2/2 R. And then there's contribution from vibrational motion, but and at low temperatures, even at low temperatures, those tend to be relatively small. But you're not. This is just an estimate. Okay, you're not going to get an exact number here, but there's a contribution from vibration there. It's going to be R. How many vibrational modes would you have? 3 times 3 minus 5, 4. So that 4R kicks in at very high temperatures. So this is the vibrational contribution would be anywhere from 0 to 4R. Okay, where the 4R is the high temperature limit. What would it be for a methane molecule? CV is approximately equal to, contribution from translation is how much? 3/2 R. Contribution from rotational motion is, this is not a linear molecule, also 3/2 R, plus contribution from vibrational motion would be anywhere from 0 up to, let's see, 3n minus 6 is how much? 3 times 5 minus 6, so that's 9. So 9 up to 9R, anywhere from 0 to 9R, depending on what the temperature is. The high temperature limit would be 9R. Okay, but at low room temperature should be close to 3R, but you may just add it. It'll still be off a little bit. How can we look up those heat capacities, by the way? A good place to look for them is the webbook, NIST webbook. Let's see, webbook.nist.gov. Clear out. See, this thing gives you heat capacity data. Okay, chemical information. And so, if you click chemistry webbook, let's say we wanted to do carbon dioxide, CO2. Okay, gas phase, thermodynamic data, search. What do I have? Here's a formula for the heat capacity. This is heat capacity at constant pressure. Okay, these are actual experimental data. Okay, so heat capacity at constant pressure of 1 atmosphere is given by this formula. This is called the Shomate equation. And so it's A plus BT, okay, and T here is temperature in Kelvin divided by 1,000. Okay, so A And your constants are given here for carbon dioxide. Oops. Down here. These are your constants in the Show-Mate equation, A plus A, B, C, D, E, F, G, H. So these are the values of the constants fitted from 298 to 1200 Kelvin. And if you're interested in the 1200 to 6000 Kelvin range, these are the numbers that you need. Okay, so your Show-Mate equation expresses the heat capacity at constant pressure, at 1 atmosphere pressure in this particular case. So that superscript 0 there, that means standard pressure, actually 1 bar pressure, okay? And standard 1 bar pressure. And this is your heat capacity right here. So if I were to do Q from T1 to T2, what would I plug in here? I'm going to put A plus BT plus CT squared plus DT cubed plus E over T squared dt. I'm going to integrate that, plug in all those constants, okay, and integrate from T1 to T2. But this is at constant pressure. How do I get heat capacity at constant volume? So CP is this one. How do I get CP? If I assume it's an ideal gas, what's the relationship between CP and CV? CP minus CV equals NR. Okay, this is a very important relationship to remember. We talked about this last time. So whatever CP is, CV is just going to be equal to CP minus NR. CV is going to be less than CP. Okay, if it's per mole, then your N will just be 1, right? So CP per mole is just going to be CV per mole minus R. All right, and these numbers given here are per mole, heat capacity per mole, joule per Kelvin per mole. All right, so on your test, you might expect me to ask you to look things up from tables. Okay, so that's a good place to know. All right. Now, let's talk about phase changes, heat flows associated with phase changes. Heat flow does not necessarily involve a temperature change. So let's see what happens when you heat a pure substance, for example, from this applet right here. Let me do a search for that. I don't have the shortcut. Get rid of all of this. Do a search for cam.davidson.edu, and you do a search for heating curve. Right there. So you scroll down to the bottom of that page. Here's an illustration of what happens when you heat a pure substance. Okay, I'm going to press this heat button right here. It's not ready yet. Okay. I'm going to press this heat button and see what happens as I'm heating the substance. I'm going to reset the experiment. Okay, so let's pretend now this blue block here is a solid. Okay, and as I heat it, what happens? Temperature goes up. This is temperature versus time. Okay, and it starts to melt. So that blue turns red there. That's just to indicate that it's melting. It's just an illustration. And what happens while it's melting? I'm still heating it, but the temperature is staying constant. That's in fact how you can tell you have a pure substance. It's got a very sharp melting point. The temperature remains constant while you're heating. So as I'm heating it, okay, it's melting, temperature remains the same. We are at the melting point. If this was water, what temperature would this be? 0 degrees. Okay, so the melting point of ice is 0 degrees Celsius, freezing point of liquid water. Now continue heating, what happens? Eventually, all of the solid gets melted, And now it's all melted. What happens now? Temperature is going to start to rise again. You're heating the liquid this time. Okay. And then once the liquid starts to vaporize, so now your red's turning yellow, what happens? The temperature remains constant again. That's your boiling point. Okay. And once all of your liquids vaporize, what happens? Temperature starts going up again. Okay. So how do we calculate the Q for this from this point to this point right here? What's Q for that? It's going to be integral of the heat capacity of the liquid, Cp, right? Constant heat capacity at constant pressure, Pt, from what's our initial temperature here? Around what, 60 to 150 maybe? Okay, and the Cp that you have here would be for the Cp of the liquid, right? Which most likely is not going to be constant. It's going to vary a little bit with temperature, so you can look up what the expression for Cp is in terms of temperature. All right, and for this part right here, what's the formula for Q? Integral of Cp dt from 0 degrees Celsius to maybe 60 degrees Celsius. Let's assume it's melting at 60. This is Cp of the solid. Okay? And now at this point right here, while it's melting, what's Q for this? Q for that is known as the delta H of fusion, or the heat of fusion. Okay? And so during the melting process, heat does flow into the system, and during vaporization, what do you call the Q for this process? It's known as the heat of vaporization, so delta H vap. Okay. So phase changes involving a pure substances at constant pressure and temperature are endothermic. Okay, so when these things happen right here during the melting process, you're heating it, so that's an endothermic process. So melting is endothermic, vaporization is endothermic. Okay, the heat involved when solid turns to a liquid is called heat of fusion. Okay, represented by that symbol. Solid to gas, sometimes a solid might change directly to a gas without turning into a liquid, so the heat for that would be called the heat of sublimation. And if for your liquid turning to a gas, the heat involved there would be heat of vaporization. Those are all positive values of Q because those processes are endothermic. Now, if you have the reverse of these, freezing, liquid going to solid, the heat would just be the negative of the heat of fusion. Okay, it's going to be a negative number. And if you have a gas turning into a liquid, then the heat flow there that's involved would be just the negative of the heat of vaporization. So these are exothermic processes. Gas turning to a solid, the heat flow there would just be the negative of the heat of sublimation. Okay. So those are exothermic processes. All right. Let's look at some qualitative questions here. A person with a fever at 38 degrees is given an alcohol rub. As the alcohol evaporates, Q for the alcohol is blank and Q for the person's skin is blank. Alcohol vaporizes. So for vaporization, Q is positive. Where does the heat come from? From the person's body, from the person's skin. So Q for the person is negative. Okay. A quick way to get your fever down. Which of these is endothermic? A, B, or C? Liquid to gas, that's vaporization, that's endothermic. Okay. Liquid to solid, this is exothermic. So when ice when liquid water freezes, it has to lose energy in order for it to be frozen. Okay, gas to liquid, condensation. That's an exothermic process. So when steam condenses into boiling water, it releases a lot of heat. In fact, okay. In fact, so steam is more dangerous than boiling water. Okay, because when water condenses from a gas to a liquid, it actually releases heat in it. Right. So you can calculate Q for converting 1 mole of steam at 100 degrees to liquid water at body temperature. So you have water turning from gas to a liquid at 100 degrees. Okay. The Q for this is equal to the negative of the delta H of vaporization. And then what's the Q for this? Transforming water from 100 degrees Celsius to 37 degrees. Q for this is just going to be C delta T, negative C. It's just going to be C delta T, right? And if we assume C is independent of temperature. So let's calculate that. Is it time to go? What's delta H? Delta H vaporization of water is 40.7 kilojoules per mole. Okay, so let's do 1 mole of steam. So delta H would be for the condensation would be what? 1 mole times negative 40.7 kilojoules per mole. So it's going to be negative 40.7 kilojoules. All right. Let's look at Q. To go from 100 degrees Celsius to 37 degrees Celsius, which is your body temperature. Q is equal to heat capacity of water is how much? Okay, 4.184 joules per gram Kelvin, right? What's the mass of the water? 1 mole of water, 18.02 grams per mole, right? What's our temperature change? 37 minus 100, delta T is 63, negative 63, right? Negative 63 degrees, 63 Kelvin. So 4.184 times 18.02 times negative 63 equals negative 4.75 kilojoules. Okay, times 10 to the third. So that's negative 4.75 kilojoules. Compare that to negative 40. How much bigger is the amount of heat released by just the condensation? About 8 times at least, 9 times. So the condensation of steam produces about 8 to 9 times more heat, releases that much more heat than just boiling water to go back down to room temperature. Okay, so that's why if you want to sterilize things, you use steam is better for sterilization than boiling water because you get that much more extra heat generated by the condensation of steam. Okay, so we'll stop there.